Hello everyone, welcome again in Eng-Man YouTube channel. Right now we are going to create Sakarot palm model in Pipesim software, so it's a very interesting topic. But before we start, I hope you subscribe, like, and share the videos to your friends because each of your support motivates me to work further to create contents like this. All right, so now we will model a rod pump, but the assumption of what we do today is that you already have a good understanding of the design or the optimization or the operation of a sucker rod pump or beam pump. All right, because if you already know about that, it will be better for us to start simulating or modeling the well. All right. Right now in Eng-Man, I still don't have any content regarding the Sakurot pump, but hopefully in the future I can make contents about this artificial lift system so that by learning about the concept, the design, and then the optimization approach, and then combine it with the knowledge to model the well, it will be much better. All right. So this is the Pipesim window. We start from general, well name, SRP or Sakurot pump. It is an active well. Well type, of course, it's a production well. Check valve setting. Still, we use block reverse. We don't want the flow back from the flow line coming again into our well. So we use block reverse as our check valve setting. Comments, you can type in anything that is important regarding the simulation. Tubulars, we are going to have casing and tubing. And I'm just going to copy paste my value and then you can follow. I'm sorry. All right, let's try once again. All right, so we have constructed our casing and our tubing. So you can do like you copy your value from your spreadsheet and then paste it here, or you can also type in manually, and you can also take your casing and tubing from the catalog like this one. So this is the catalog. You can just type in the outer diameter or the ID, all right, anything you like. And then we go to deviation survey. So we will have two-dimensional, and then I'm just going again, copy paste my value. And then it will be plotted like this one, TVD or true vertical depth against horizontal displacement. Wellhead depth, 0. And of course, bottom depth, 10,000 feet. Okay. Also, you need to know that Sakurot pump will perform best actually in a vertical well. If you have a deviated well, there will be maybe a problem. Maybe there will be friction between the tubing and your rods, right? Where the rod is going upward and downward, there will be friction. But right now it's okay. We will still try to construct a deviated well because in general, actually, we still have a lot of deviated wells equipped with Sakurot pump. All right. And then let's see the validation message here. Well, it's not solvable. No valid flow path can be found. All right, it's okay. And then we go to downhole equipment. We will have packer here in this example, oddly enough, because usually we don't equip our well, which will have Sakura pump with packer, because it will disturb the separation between the liquid and the gas. Because we will have multi-phase here coming from the reservoir or from the perforation, and the gas will be separated and go upward through the annulus. So it will be better if we don't have any packer in our Sakurot pump well. But in this situation, in this particular example, I'm still going to install packer in my well. All right. So the depth will be of this value. Okay. And then of course we will install artificial lift. We press new here. You see the default is PCP or progressive cavity pump, but we would like to select rod pump. Okay. And then we install it at depth of this value. And you can see here, right? Okay, this is the icon of our rod pump. And then you can now design your suck rod pump. We will input the performance data in nominal rate or stroke length and frequency. I will prefer this one, and then I will define the operating parameter. At this point, you need to understand the basic concept about the design of suck rod pump. All right, hopefully we can learn together in the future. But right now, in this particular example, you can follow me. Strokes per minute. I'm just going to input 12. It means that the suck rod pump during the operation or during the production, it will have 12 strokes per minute. And then the stroke length will be 108 inch. The plunger diameter of this value. Slip coefficient, this is important. I'm just going to input 0.002. Maximum DP. Actually, you can leave it blank because the mandatory input will be highlighted by these red lines. Okay, so you can just leave it blank, but I'm just going to input some value here. So it's okay. 300 horsepower. Pump efficiency, let's start with 70%. So we will have a quite leaky pump here. Drive rod diameter. So this is the diameter of the suck rod. Or here in Pipesim, it is called drive rod. And then for the calculation options, gas separator present. Yes, I would like to install gas separator here with separator efficiency, not 100%, not that perfect. So let's use 80%. And then I don't want to recombine gas at wellhead. All right, so far so good. Okay, and then let's go to heat transfer. I will select multiple and again multiple, and I'm just going to copy paste my value. All right, we will have also the plot here. And then of course the completions. The main part of this simulation, of course, the inflow part coming from the reservoir into the wellbore. All right, so it will be named CPL or completion. It's a vertical well, single point, and then the middle of the perforation, it's important. It will be located. Okay, then you will see here, this is the icon of our perforation, and it will be the flow path. First coming from the perforation, go up, and then into the intake of our rod pump, and then go up again into the tubing, and then into the wellhead. All right. So for the reservoir pressure, 1800 psia, reservoir temperature of this value. Of course, the IPR basis will be liquid. And then, first, I would like to have Vogel equation here. Also, you need to understand about the Vogel equation, but it's quite easy. Vogel to construct the IPR, the AOFP or absolute open flow potential. I would like to have the well to have this maximum flow rate. 520 stock tank barrel per day. Vogel coefficient, normally it will have value of 0.8. All right. So we still don't have the IPR curve here because we still don't implement our fluid model. So we go to fluid model, click new, we select light oil and gas. Okay, I will call my fluid model oil, and then we go edit. All right, let's have the water cut value to be 50% and the GOR 300, SCF per STB, and then gas specific gravity 0.67, and then water specific gravity 1.03, API of the oil 32. We will have CO2 here. Let me check my value. So as the impurities, we will have CO2 and nitrogen. Okay, close. All right. And then we will have our IPR curve looking like this one. All right. And then at this point, you need to check the validation message. It will be shown whether or not you will have something that needs to be corrected before you go to nodal analysis. At this point, we are validated. We are okay to go to further analysis, which is the nodal analysis. We go to home, and actually, if you want to do sensitivity analysis to select the best outflow correlations, you can go to simulation settings and then go to correlations. You can select either Hagedorn and Brown or Bex and Brill and other correlations, which you can select the equation or the correlation that is suitable for your well or for your field. Okay, in this particular example, I'm going to choose Hagedorn and Brown. Okay, and then we close. All right, so far so good. Now we are ready to do nodal analysis. And also lastly, before we go to nodal analysis, you can also model your surface equipment. Maybe you will have flow line and choke and other things, but right now I'm just want to focus on the well. Okay, so I'm just going to leave it like this one. We go to nodal analysis. Of course, select location bottom hole, and then you can see we will have nodal analysis point at the bottom hole. All right, at the perforation depth. Okay, so let's see. This is the nodal analysis window. Branch start, we start from the reservoir. Okay, so the inflow will come from the reservoir. Nodal point will be at this location, at the bottom hole. And then the branch end or the downstream or the outlet will be the wellhead. All right, so this is the correct locations for our nodal analysis. As a petroleum engineer, as a reservoir engineer or production engineer or subsurface engineer, we would like to analyze. As a petroleum engineer or production or reservoir engineer, we would like to focus on the well. So this is the correct or this is the proper locations for our nodal analysis. Coming from reservoir and then do the analysis at the bottom hole, and we will have the outlet at the wellhead, right? At the upstream before the choke, if you have choke. So the outlet pressure here will be the wellhead pressure. Let's say I'm just going to apply a typical value for onshore well, which is usually 100 psi. Okay, we are ready to run the nodal analysis. And then we will have the inlet conditions, the completion data, reservoir pressure, 1800, and then this temperature. Just run using this scenario, no sensitivity analysis. Let's see. So we will have the IPR based on our completion data, and the outflow will be generated using the data that we input at artificial lift section. All right, so this will have, we have this blue curve. This is the IPR or the inflow performance. And then we will have this outflow or tubing performance or the vertical flow correlations, right? You can see because we have Sakurot pump here, which is a displacement pump, the outflow will have shape like this. All right, so you go like horizontal way and then go sharply to be a vertical trend. And then our operating rate will be around 200 stock tank barrel per day. Whereas the bottom hole flowing pressure will be about 1300 psi. So this is the base scenario using data from completion or from the inflow section and data from the artificial lift or from the outflow section. You can also do sensitivity like this one. Let's say our reservoir pressure decreases, okay, from 1800, sorry. So let's see the reservoir pressure from 1800 go down to just 1000. Let's see how the IPR will be. Yes, you can see, right? Like this one. So this is the line or this is the IPR for reservoir pressure of 1800. You can see here. Okay. And then this is where we will have our reservoir pressure down to just 1000 psi. We still can flow. You can see there are cross sections from VLP and the IPR. All right. So Sakurot pump is very dependable. It's quite reliable to flow the reservoir or to flow the well down to very low reservoir pressure. It's a good, it's a tough artificial lift. The only problem is you will have like friction between your rods with the tubing, and maybe the flow rate will not be that high compared to gas lift or electrical submersible pump. So this is the sensitivity for the inflow, but let's see if we have sensitivity coming from the outflow part. Of course, I want to do sensitivity from the rod pump, and we would like to first analyze about the slip coefficient. It represents the leakage, how severe the leakage in your rod pump, all right? Or maybe how is the efficiency of your rod pump, okay? I'm just going to copy my value, okay? Let's see, run. Okay, if you have higher slip coefficient, it means that you will have higher leakage or more severe leakage. You can see the outflow will change. All right, we start from the line curve, okay? The 0.002 stock tank barrel per day per PSI, the slip coefficient. The slip coefficient is lower, which means that the leakage is smaller also, and then the efficiency, of course, will be higher. So this one represents the higher pump efficiency, whereas this green line represents the higher slip coefficient, which means more severe leakage or lower pump efficiency, the volumetric efficiency. Okay, so hopefully it can be clear for you. And then lastly, just do sensitivity for the, let's see, of course, what about the strokes per minute? 8 strokes per minute, and then 10 strokes per minute, and then 12 strokes per minute. These are the typical parameter, or these are the typical conditions for the operation. Run. All right. Okay. This is very, very interesting. Designing artificial lift in Pipesim is very interesting. It's quite easy. Okay, just wait for the last line. All right, so you can see now we already constructed the sensitivity analysis. We vary the stroke per minute. This orange line, of course, the 12 SPM or stroke per minute will result in higher flow rate. The green line shows the 10 SPM. And lastly, the red line shows the 8 SPM. All right, it's very interesting. And lastly, I want to show you the profile results. Just go to profile results. It will show you the profile of the pressure starting from the completion or starting from the reservoir, 1800, and then go to perforation or bottom hole, and then goes up to the pump. And then, of course, it will be pumped and the pressure will be significantly increased to this level, higher than 3000 psi. And then starting from the discharge of our pump, it will goes up to this wellhead depth at 0 feet. Okay. And I've stated that the outlet pressure or the wellhead pressure will be 100 psi. And you can see go below, the value will be 100 psi. All right. So this is the pressure profile. This is the engine console. And this is the IPR and VLP or the nodal analysis section. All right. So far, so good. So we can conclude now. We close. All right. So in this example, we have constructed nodal analysis for a Sakharov pump well. All right. We've construct the tubular, the equipment, and then we also construct the inflow performance using Vogel equation. We design the Sakharov pump, and then we do the nodal analysis. All right. I hope you enjoy the video. I hope you can learn by yourself by looking or by watching the video. I hope this is useful and see you in the next video. Thank you.